Now that we understand what linear inequalities are and how to graph them, we're going to move on to systems of linear inequalities. And it turns out that this is basically going to be the same process. We're just going to graph our linear inequalities in the system over and over and over again. So there's not a whole lot new in this section. It should be a fairly quick section. But this is what we're going to look at. We're going to look at systems of linear inequalities in two variables. We won't proceed beyond two variables in this course. Well, at least not this week anyway. Yeah, I think the best way to teach this is just by example, so we'll just jump straight into an example. Solve the following system of linear inequalities graphically. So here's our system. 3x plus y less than or equal to 21, x minus y less than or equal to 20. And like I said, we're just going to work with both of these equations separately for now. So I'm just going to give them a label 1 and 2, and I want to graph both of them. So let's see. These are given in standard form right now. I think I work better with lines. I think about lines better when they're given in solve for y. So give them in slope-intercept form. So let's just go with number 1. What's my boundary line? Right, if I solve for y, I would have y equals minus 3x plus 21. And so I'm isolating y there, and I'm changing this less than or equals to an equals. And number 2, what's my boundary line? Again, solving for y, 2y is equal to x, so y is 1/2 x. Check that if you don't believe me. And then just converting the inequality to an equality. So there's our two boundary lines. And let's graph them. So our two boundary lines. Let's see, y equals 1/2 x, that's an easy one. That just cuts through the origin with slope 1/2. So there's y equals 1/2 x. And the other boundary line has y-intercept 21, slope minus 3, looks something like this. I'll label it 21. This turns out to be 7 if you think about it. Set y equal to 7 or y equal to 0 and solve for x. There's 7. Doesn't really matter though, but here's the boundary line. Y equals minus 3x plus 21. Okay, so now let's plug in some test points. Number 1, test point. What do we want to do? Well, here's my boundary line. The origin is not on the boundary line, so we can just plug in 0, 0. And we'll ask, is that a solution to this inequality? So 0, 0 is 3 times 0 plus 0. Is that less than or equal to 21? Well, is 0 less than or equal to 21? Yes, it is, right? So the origin is a point on the graph. So the graph of number 1 is this lower half plane. What about the second one? We need to choose a test point not on this line, on y equals 1/2 x. So I can't go with the origin because the origin is on the line. How about I just go with the 0 and 1, right? So we'll choose this point right here. 0, 1, x coordinate 0, y coordinate 1. And we'll ask, if I plug it in, is 0 minus 2 times 1, is that less than or equal to 0? Well, what does that work out to be? That's minus 2. Is minus 2 less than or equal to 0? The answer is yes. So this test point is indeed in the half plane. So the solution to equation number 2, the graph of equation number 2 if you want, is the upper half plane that includes this test point. So all of this. All right, so everything in yellow is equations to, or solutions to equation number 1. Everything in red is solutions to equation number 2. When we talk about finding solutions to a system of equations, we want points that satisfy them both simultaneously. So if I took this stuff that's only in red, right? If I took this point right here, this is not a solution to equation number 2, but it is a solution to equation number 1. If I took something down here that's only in yellow, this would be a solution to equation number 2, but not a, or, am I getting this the wrong way around? Yes. This point right here that's only in red is a solution to equation 2, but not a solution to equation 1. If I took this stuff only in yellow, this is a solution to equation 1, but not a solution to equation 2. But if I look at this overlap region, the stuff that's in yellow and red, that satisfies both equations simultaneously. So it turns out that this stuff, the overlap, that I'm now shading in white, that is the solution set to the system. All right, so the set of solutions to the system is the overlap. And it's the overlap of the half planes given or defined by each inequality. Alright, so it's everything that I've shaded in white here. It's the stuff that's both yellow and red. Why? Well, because those points satisfy both equations at the same time. This stuff is sometimes called the solution region or the solution set. Also the feasible region or the feasible set. So called the solution set / region, or the feasible set or region. Our textbook seems to prefer the phrase solution set, but then they're very strange. Then you look at the homework, then they start using this word feasible set all over the place instead. So we just use both, and I'll indicate that, or I'll point out that both of these mean the same thing. All right, it's the solutions to the linear inequality. There's one more thing that's actually really important about this set. So what's the boundary? The boundary of this set is this stuff and this stuff, right? These two lines. Well, these two lines meet at this point. And for reasons that we'll get into, this point right here is very important, right? So this is sometimes called a corner point. So there's a corner point, and I want to know its coordinates. Let's see. I don't want to erase too much, but let's just quick definition. Quick definition: a corner point is the point of intersection of two boundary lines. So we'll solve, we only have one corner point in this example, but we'll solve for it. So in this example, how do I find the intersection of two boundary lines? We set them equal to each other, right? So we've got minus 3x plus 21 is equal to 1/2 x. What do I want to do now? Probably multiply both sides by 2. So minus 6x plus 42 is x. Let's keep everything positive, so we'll add 6x to both sides. 42 is 7x. And what does that mean? That means x is 6, I believe. X is 6. If x is 6, what's y? We'll plug it back into either of these equations. This one's really easy. If x is 6, y is 3. 1/2 of 6. So our corner point has coordinates 6 and 3. Again, for theoretical reasons in the next section, we'll see why finding the corner points is really important, but for now it's just important to point out what they are. It's the intersection of two of the boundary lines and being able to find them. All right, so there's the coordinates of this corner point. I'll also point out that it's possible, since we're looking at overlaps of planes, we might have a whole bunch of, or overlaps of half planes, we might have a whole bunch of different half planes if we have a whole bunch of different equations to work with. And it's possible that the overlap is an empty set, right? If you look at where they all overlap, you don't get anything at all. So that could happen, right? The solutions to, or the solution set for a system of linear inequalities might be empty. That can happen. Let's do another example though. Okay, here's our example. Solve and find all corner points, and we've got a system of linear inequalities in two variables x and y. We have 5 equations here, but I really only have to think a whole lot about the first 3, 1, 2, and 3. These last 2, 4, and 5, what do they say? They say x is bigger than 0, so that means I want to look at everything to the right of the y-axis. And y bigger than 0, I want to look at everything above the x-axis. Right, positive x values, positive y values. This tells me I'm looking for a solution set in the first quadrant only. And sometimes these will be called non-negative restrictions or non-negative constraints of the system. So these are the non-negative constraints. And it just means all I'm doing is I'm looking in the first quadrant. First quadrant only. Right, because equality x equals 0, y equals 0 gives us the 2 axes. Okay, so what do I want to do? I want to proceed just like we did in the last example. I want to graph all 3 of these inequalities and find the region of overlap of all of the 3 half planes. So I'm probably going to need a lot of working space. Equation 1, the boundary line would be y equals minus 5x plus 20. So let's try to graph some stuff here. Y equals minus 5x plus 20. What is that? That's a line with y-intercept 20. Slope minus 5. If y equals 0, x would be 4, right? So this is just this line right here, from 20 to 4. I'm only going to draw this portion because, again, we're only looking in the first quadrant. I'm just going to draw the boundary lines really quickly. Then we'll worry about what the half planes are. Number 2, we've got y. If I make this equalities, y equals minus x plus 12. What's that? That has y-intercept 12, slope minus 1, x-intercept, if y is 0, x is also 12. And last but not least, number 3, y equals what? 3y would be minus x plus 18, then we divide both sides by 3, this would be minus 1/3 x plus 6. So this cuts through here, it's 6, has slope minus 1/3, I believe this would give me 18 as my x-intercept. So there's 18. Alright, so let's label these really quickly. This equation, y equals minus 5x plus 20. It's number 1. This guy is number 2. Y equals minus x plus 12. And last but not least, this one is number 3. This is y equals minus 1/3 x plus 6. Alright, there's my 3 boundary lines. Now I need to figure out which side we're looking at. So let's choose, the origin's not on any of these lines, right? So how about we just plug in 0, 0? Let's do this mentally. let's do this mentally. Plug in 0, 0 into the first equation. What do I have? I've got 0 is bigger than 20. Is that true? Is 0 bigger than 20? The answer is no. Alright, so I'm not looking at this side of this line, I'm looking at this side. So I've got all of this. Let's come to a second equation. Plug in 0, 0. Is 0, 0 less than 12? Is 0 plus 0 less than 12? The answer would be yes. So for line number 2, we're looking at everything under line number 2. Line number 2 is this one, so we're looking at everything under here. I did a really bad job of not overlapping these. Oh, sorry. This is part of it. There we go. Okay, and last but not least, equation number 3, plug in 0, 0. Is 0 plus 3 times 0, so 0, is that bigger than 18? The answer is no, right? So 0, 0 is not in the solution set for this third equation. So once again, we're looking at everything above this line. So let's try to combine all this. Everything above this line, so everything in red, everything below this line, everything in yellow, and then once again, everything above this line, which would leave me with, it looks like, just this little region right here. So this is our solution set. That shaded little triangle in white. So here is our solution set, or feasible set, feasible region. And this accounts for a graphical solution. We've now found the region in the plane where all the coordinates x and y satisfy all 5 of these equations simultaneously. There's a little bit more to this question though. Find all of the corner points. So I need to find the coordinates of this point, and this point. But this should be nothing more than a bit of algebra here. How do we find these points? Let's see, I want to, this point right here would correspond to setting equation 1 equal to equation 2. So setting equation 1 equal to equation 2, we're going to have minus 5x plus 20 equals minus x plus 12. Let's keep the x's positive, so we'll add 5x to both sides. So we'll have 4x on that side. We'll subtract 12 from both sides, so that gives me 8 is 4x, or x is equal to 2. And if x equals 2, what's y going to equal? Well, plug it into either of these equations. How we plug it into here? If x is 2, y is going to be minus 2 plus 12, which is 10. So this point has coordinates 2 and 10. Certainly looks reasonable, right? Based on my graph, assuming everything is roughly to scale, the x coordinate here should be less than 4, 2, and it should be somewhere between 6 and 12. We got 10. So that looks reasonable. We'll just erase this because we don't need it anymore. What about this corner point? This corner point corresponds to the first line intersecting the third line. So we'll set equation 1 equal to equation 3. We've got minus 5x plus 20 is equal to 1/3 x plus 6. Once again, solve for x. I think what I want to do is get rid of that 1/3. Let's multiply both sides by 3. So we'll have minus 15x plus 60 is equal to minus x plus 18. We'll add 15x to both sides. So that will give me 14x over here. We'll subtract 18 from both sides. Will give me 42 over here. And then we'll just divide both sides by 14. Looks like 3. X equals 3. And if x equals 3, plug them back into either equation 1 or 3. If x equals 3, y would be minus 15 plus 20, which is 5. So my claim is that this corner point has coordinates 3 and 5. Again, looking at the picture, I'm expecting something between 0 and 4 for the x-coordinate, and bigger than 2, 3, and something between 0 and 5, or 0 and 6, and we got 5 there. So it certainly looks reasonable. And now we just have to do one more corner point, which is this intersection right here. This is the intersection of line 2 and line 3. So when is line 2 equal line 3? When is minus x plus 12? When do you equal minus 1/3 x plus 6? Well, once again, let's multiply both sides by 3. Minus 3x plus 36 is equal to minus x plus 18. Add 3x to both sides, so we have 2x over here. Subtract 18 from both sides, so we have 18 over here. That means x is 9. And plugging into equation 2, if x is 9, y would be minus 9 plus 12 is 3. So here is the point 9 and 3. So yeah, there's our 3 corner points. We have, and again, this looks reasonable, right? We were expecting something between 4 and 12 based on this picture. We got 9, and something even less than this y-coordinate, which is 5. We got 3. So here are the 3 corner points. Once again, I want to point out that you can have empty solution sets. Right? Suppose I just threw a 4th equation in. Right? Suppose I threw a 4th equation in. So I already know the solution, or everything that satisfies all of these equations is this little region right here. Suppose I threw a 4th equation in that was, say, this line, and the solution to that was everything above this line. Well, now my overlap would be everything above this line and everything in here, and there are no solutions. All right, so keep an eye out for that. I'm not doing any examples, but it is possible to have empty solution sets. And there's just one more thing I want to point out. So I will leave this on the board. But I'll really quickly try and sketch our last example again. Last example, we had a solution set that looked like the following. It roughly looked like this. Okay, so I'm just comparing these. I've got this solution set here. I've got this solution set here, and this solution set here, and these are very different in nature. Something about their shape is very different. And the difference is that this one is sort of infinite, right? It's infinite in size. It extends off to infinity. Meanwhile, this one doesn't. It's finite. It's what's called bounded. So this is bounded, and this one's not. And a formal way of describing this, or perhaps slightly informal really, is saying that a solution set is bounded if it can be enclosed within a circle. If you can draw a circle that encloses it. So here's a circle. Here's a circle that encloses my solution set. But no matter how big of a circle you try to draw here, no matter how big you try to draw, your circle will never be large enough to enclose this entire solution set. Alright, so this is our definition we're going to go with. Definition, a solution set is bounded if it can be enclosed within a circle. If it can't be, it's unbounded. So otherwise, it is unbounded. So this is trying to get at this idea of, does it extend off to infinity or not? And if it doesn't, then you should be able to draw a circle that's large enough that you can just enclose the whole thing, encompass the entire thing. So we've seen two examples now. Here's an example of a solution set that's bounded. Meanwhile, here's an example of a solution set that isn't bounded. I think to stop this video from getting too long, this is it. We'll just do one of these examples. We've actually done two. So this will suffice, but it's the same thing every time with these problems, all right? So graph all of your linear inequalities. That gives you a bunch of half planes. The solution set is the overlap region of all of the half planes that you have. And the corner points, if you're asked to find the corner points are just the intersection points of the corresponding boundary lines. And then you might be asked, is your solution set bounded or unbounded? Well, just ask yourself, can I draw a circle around it or not? Thanks.